Yeah, let's continue the identification with characteristic parameters with the IT1 behavior. The IT1 has the following transfer function, f of p, has a k in the numerator, that's a gain, then a pure p in the denominator, that's the integrator part, and a 1 plus pt term, this is the pt1 part of the IT1. IT1 is an I in series with a PT1. Okay, the step response can be looked in the workbook. So I open the workbook, page 16. Here in row 5 in the table on page 16, you see the IT1, that is the symbol, that is a transfer function. Here you see the step response, a unit step response. There is an exponential delay and then ending in a ramp. The ramp has the gradient k. This is k dt, and this is the time dt. So this is a triangle with horizontal ktd and vertical dt. So the gradient is k, and the delay is defined by the time constant. Okay, go back to my OneNote. What we can do is, okay, first measurement of the step response. I prefer red. So you see the starting curve has a horizontal tangent in the time moment 0 and then going up in a ramp. This ramp is the consequence of the integrator, and the exponential delay is the consequence of the PT1. So what we can do, we can draw a tangent, so the ramp could be extrapolated back to 0 time, and the time between 0 and the cross point with my ramp tangent defines the time constant t, and the gradient of the ramp, this gradient is defined by this dt and this d. Yeah, what is this? du, because I want to draw the u2 over t as a step response with a step function with the amplitude u sub o at the input. So let's continue this. Yeah, the k, go back to black color. K is nothing else than du divided by dt, but don't forget we have not the unit step response, we have the step response with input amplitude u sub o, so we have to divide the gradient by this amplitude to get the k factor of the IT1. And the t is just without any additional declaration. Here, some words to the 0. In the step response of the IT1, there is no indication where the input step is switched. So we need, for this and the next two step responses, we need a second two-channel scope. Yeah, this 0, the 0 time point must be measured with a the second channel with second channel of scope. Yeah, most scopes can trigger on this step signal, and then automatically the time base is set to 0 at the trigger point. I would like to prefer method without drawing a tangent, because a computer who wants to identify the step response cannot draw tangents. So a computer works with points. Here is also a 2-point method possible. Similar to my PT1 2-point method. Is very simple. Let's do this in green color. I try to find out the point at the end of the ramp and call the voltage at this point U2. Then a good point for my calculation is that point where the voltage is half of U2. So this is U2 divided by 2, and I call this U1. And the time point of this voltage I call T1. And with both points, I can very easily calculate, with the coordinates of the points, I can calculate the both unknowns K and T. The U sub OK is the gradient of the ramp. And now I have a triangle here from this point to that point. You see, this triangle can be used to define the gradient. So the horizontal part of this triangle is T2 divided by T1. T2 minus T1, sorry. And the vertical part of this triangle is U2 minus half of U2 is half of U2. U2 divided by 2. So this is a way to calculate the K factor. What about the T factor? The time constant is this distance from there to there is the time T2 minus the difference between T2 and T1 minus T2 minus T1. Then I am at this point, and here this part from this point to that point is again T2 minus T1. So I have to subtract 2 times T2 minus T1, and if I put this together, you see T2 minus 2 times T2 is negative T2, and minus 2 times minus T1 is 2 times T1. So the very simple equation for my time constant is 2 times T1 minus T2. This can be calculated easily. There is no module in Windows C# because this is so easy. So I have now completed the IT1 identification method with the step response. Let's come to the next point. Next point is method 8.1, then the type C, that is a PT2 identification. Let's start with the transfer function. The transfer function, the normalized traditional transfer function of a second order low pass filter is K, the DC gain, divided by 1 plus then 2 times the damping constant divided by the natural frequency times P plus 1 divided by the natural frequency squared times P squared. Da muss you have to draw there a 0. Yeah, natural frequency omega 0 and damping factor d are the characteristic values. We have three unknowns: DC gain, d, and omega sub O. You should know that if d is larger or equals 1, convert the PT2 into two PT1s. In two PT1s, then we have no oscillation possibilities. Yeah, damping factor larger one means just asymptotical change of the step response. If D is smaller one, then we have an oscillation possibility of the PT2 block. So this is a way. Now let's have a quick look into the page 16. Page 16, the PT2 block is row 3. Row 3 here has a transfer function, and you see the typical PT2 step response is an oscillation around the final value. There's an overshoot, an undershoot, and so on, depending on the damping factor. The larger the overshoot, the smaller the damping. And this is a way to come to good results. Let's draw the step response, typical step response. Again, U2 over T. There is a final value, and again in the final value the K factor is hidden. So if we can find the final value, we have with the input amplitude U sub O, we have a good indication for our K factor, or the DC gain. Then the curve has a horizontal tangent in the zero switching time. So same problem like IT1, you need the time point of the input step function to identify the 0 point here. Then there's an increase. Look, if you see this curve, this could also be an IT1, but sometimes then there is the curve, right curve, we can say, with overshoot and undershoot. So this is the typical curve, and the characteristic value. Don't note that 8.1 identification method is with characteristic values. One characteristic value is the first maximum, because we have good equations of this time point. That is Tm, and the overshoot here can be marked as delta U. And with this overshoot and the Tm time, I can, with the following equations, I can easily define the both unknowns. K is already known, but the first unknowns with the following equation. I just repeat that equation we have discussed also in control system 1. First, the overshoot, the relative overshoot, is the delta U divided by the final value, K divided by U sub O. And we have an equation where we can define this overshoot, this relative overshoot, is only depending on damping factor, and with the mathematical equations we can exactly find the relation between the U factor and the damping factor. D is negative natural logarithmic U divided by square root function pi squared plus ln squared U. So with a measured U, you can calculate the unknown of the transfer function D. Same is with Tm, there is an equation, Tm, which is pi divided by omega naught square root 1 minus d squared. So it is easy to solve this for the unknown omega naught. This is just pi divided by Tm square root 1 minus d squared. So first measure U, calculate d, measure Tm, calculate omega naught, and then all three parameters are definable. Okay, so far the PT2 identification. I think that's enough for this. So for control systems this is not so important because there are very few processes which have really oscillating behavior. Most process types has a series of a chain of PT1s. So this is a 0.81d which comes now. So come to 8.1.d chain of PT1s. So not only one PT1 is in case A with a K and a T1, but a second PT1 with gain 1 and a new time constant T2, and a third one T3, and a fourth one, and a fifth, and infinite number, unlimited number. There could be this could be a chain of n PT1s, and I call this n. And now this is ready. So we have a chain of n PT1s, and this method works with an n which is larger or equal to. If n is 1, go to 8.1.a, but n here could be any number, because now look, first, what is with the k? The k factor is a DC gain of the whole chain. Of course, each PT1 could have a gain k, but I prefer to put all k's together in a total k, which here I call k, and then I can set all other k's to 1. Yeah, k is a DC gain of all PT1s, and yeah, the DC gain of all PT1s is a product of each DC gain of each PT1. So it's no problem to put all things together, put it in 1k and set the rest to 1. Then there are n unknown time constants. And I will show you that it is nearly impossible to can identify all unknown Tn's with measurement of a step response. This is not possible. Mathematically, yes, but with noise on the signal, no. And this is also not necessary. I show you a method which is absolutely sufficient for control system purposes. Yeah, first note the step response. Looks like the following curve. Again, a time diagram. You see my computer. I have to work now with an old computer, Dell Venue. My Surface, my Microsoft Surface laptop was defect, so I have to exchange it, and this exchange process with Microsoft takes 2 weeks, so I have to work 2 weeks with this very slow Dell computer. Sorry for this. Starting with today's lecture, you will see it in my drawing and working rather slow. Yeah, okay, so far the step response of an n PT1 block has a final value. This final value is u sub ok, and the curve itself has following form. Also in the switching time 0, no indication of the switch. Then an increase with a, say, left curve. Then an inflection point, and the curve turns to the right curve and ends up in the final value. Here again we have a final value. And this curve looks similar to this. We call this S curve. S curve. Independent if you have 2, 3, 4, 5,000 or any number of ends, the curve looks always the same, and then you can understand why, if the form is always the same, there is no method to identify different time constants. So the way we want to go on is we want to measure not the single time constants, but we want to find a model which fits to our original process. And this works in this chapter with the inflection tangent. What is an inflection tangent? An inflection tangent is the tangent in the steepest point. Look here, this in my drawing is the steepest point. I draw now the tangent, manually tangent. This tangent crosses the 0 axis at tu, so this time here is tu, and crosses the final value. So for this purpose you need to know the final value. This time range is called Tg. And now with this both manually derived times tu and tg, it is possible to calculate the following model. So I can say identified model is always the same as a 2pt1 model with gain k, which comes from the final value, and a ta, a new time constant ta, and tb, second new time constant. Sometimes this 2pt1 model, I have told you that the form of the step response is the S-curve, independent if you have 2, 3, 4 or 1000 t's. So sometimes you can find a model with 2 time constants which fits to your npt1 system, but sometimes 2 time constants are not sufficient. Then a better identification can be done if you add now a delay time block 1, and this is td for delay. Td is a delay time. Okay, how can we find now Ta, Tb and Td? This is a method from a book, from a German book with the author, which is called Reuter. Mr. Reuter, can't read it. That's, I think, from Reuter. You don't need the book because I can show you how this works, and then I give you a computer module which can do the job for you, but the background should be clear. So I show you how Mr. Reuter works. I show you a table from the book. Yes, in this book on page 66, it doesn't matter, there was a table, and look what this table contains. There are 3 main columns and some rows. The first column has a ratio Tu over Tg, which I have measured. So here I can look up the ratio of both times, and you see this table ends in 0.104 because this is the highest ratio which is possible with two PT1s. And Mr. Reuter found out that the ratio TU over TG depends directly on the ratio TB over TA. There is a clear coincidence between both ratios, and he calculated this with a computer, and intermediate values can be found up with interpolation. And if you know the TB over TA, look into the third column. Here you can find the TG over TA. So measure TU TG, look in the, find the row, then read TB over TA and read TG over TA. With this value, TG is known, you can calculate TA, and with TA here, with this value, you can calculate TB. So this is a manual way, but you see this is uncomfortable, so I have developed a small C# module in WinDF C#. You can find it, the Reuter identification module, which does a job for you automatically with program background. So, but the idea is clear. You have to measure TU TG, put the numbers in, and calculate then a TA and TB. I show you how to do this, and then we make an example. Yeah, for this purpose, start WinDF C#, go to identification, and in the identification you can find in the second menu point the Reuter 2PT1 identification. And this module gives you some information. Here's a picture to tell you that what is TU and TG. Put then the numbers into this field, and then if you ends up the values, automatically the program calculates T1 and T2, that are my TA and my TB in the lecture, and sometimes a delay time is necessary. Yeah, if the ratio is larger than 0.104, then this program automatically adds a delay time. So the TU was then separated in two parts. One part goes into a delay, the other part goes into the 2PT1 model. So this is a very simple way. Yeah, just start this program, click on this menu point, and then type in your both measurement values, and the rest comes automatically for your system. So I end up this video with the remark C module WinDF C#, and then identification menu point. Menu point identification, and then Reuter. Next video you will see an example.